All right, this is Math372 complex analysis. This is lecture 22. This is the thou shalt lecture. So thou shalts are commands that when you see something, you should do something. What is one of the thou shalts you should have after taking a class with me? I'm sorry? Good. If thou seest a product, thou shalt logify it. All right. If anybody knows any English professors, you are, of course, welcome to run this by them, or you could actually talk to, I guess, some professors in the religious department. I want to introduce another one. If thou seest a holomorphic function, thou shalt. Now this is a hard one. Any idea what you should do when you see a holomorphic function? Haven't done too much of this, but we have seen it once or twice. Thou shalt take, is it maybe thy or thine? Oh. We'll take the contour integral of its logarithmic derivative. So basically, f goes to something like this. And this is one of the big ideas in complex analysis, is taking logarithmic derivatives and integrating them. Now, the Riemann Zeta function is defined as the sum n goes from 1 to infinity of 1 over n to the s. And it turns out it's also the product over primes of 1 minus 1 over p to the s inverse. All right? Today we're going to basically do a rough proof of the prime number theorem. We're going to do the key ideas. The argument I'm going to give you will not work today. And then we'll see what do we need to actually make the proof correct. But you can see roughly what's going on, why this has a chance, and why we should discriminate amongst the primes. Not a huge amount, but a small amount. Okay? We have two different formulations for the zeta function. Which one of them do you think I will prefer? The one on the right. Because if I do anything involving a log, the log of a product is the sum of the logs. That's going to work extremely nicely. F prime over f, this is really the same as the integral of d by dz of log of f. Because if you take the derivative of the log of f, you get f prime over f. Or if you want 1 over f times f prime, if you want to write it that way. Where have we seen integrals of f prime over f before? The argument principle. And when we do integrals of that, we count zeros and poles. So what we're going to do is we're going to do something very similar to this, except instead of integrating f prime over f, we're going to put in a weight function. And then that way, the zeros and the poles will be weighted by whatever this function is. And when we look at this, we could take the derivative of either one. But if I want to take the logarithm and then take the derivative, the sum scares me. The product, however, is very nice. So the log of zeta of s is going to be negative sum over p log 1 minus 1 over p to the s. And now if I take the logarithmic derivative, I'll get zeta prime of s over zeta of s. And then this is where it's really nice to be doing proof in quotes. So what don't I have to worry about right now? Yeah, differentiating term by term. I can, yeah, it's not a problem. So it'll be minus the sum over p. Now I take the derivative of the log of 1 over, so I get 1 minus 1 over p to the s down below. And now I have to take the derivative of the top. So this is p to the negative s. P to the negative s is e to the negative s log p. So I'll get a log p and then a p to the minus s. Any thoughts how I should handle this infinite sum? What could I do? Do a geometric series expansion. And so this will become negative sum over p log p over p to the s. That's from the first term. Plus what I will call good of s, everything else. So this is from a geometric series. Keep only the first term. All right? So when we do a geometric series, we'll have this over here will become 1 plus 1 over p to the s plus 1 over p to the 2s plus 1 over p to the 3s. So the p to the minus s, that's giving us this piece. And then everything else will be like 1 over p to the 2s, 1 over p to the 3s. As long as the real part of s is large, that's going to converge well. In fact, if the real part of s is greater than 1/2, then 1 over p to the 2s, and this is where the notation is absolutely horrible, 1 over p to the 2s would be like a p series with p greater than 1. Okay? The notation is unfortunate, but all the other terms will be fine. And so this part you can just handle. So now what we're going to do is we're going to integrate. I'm going to move the minus sign over. Negative zeta prime of s over zeta of s. I'm going to multiply by x to the s over s ds. And this will be the same as the sum over p, the integral of log p. I'm going to write it like this. Log p times the integral of x over p to the s ds over s plus. So the integral of good becomes nice. All right? That stuff can all be handled. All right? Let's look at what's going on. I need to choose where I want to integrate. Let me start by maybe integrating over the real part of s is equal to 1 plus epsilon. And if I integrate there, then everything is going to converge absolutely. Everything is fine. And this part will be easily manageable. What I want to do now is I want to complete the contour. So if you look at what's going on, here's 0, here's 1 plus epsilon, here is 1/2. We talked about the last time using this alternating zeta function. It's also called the Dedekind zeta function, which gave us a continuation of the zeta function to real part of s greater than 0. And we saw it had a simple pole at s equals 1. We can now look at this continuation. And so what you typically do is you integrate up to big IT coming from minus IT all the way down here. So this would be 1 plus epsilon plus IT, 1 plus epsilon minus IT. And then ideally, what you would want to do is you would want to go all the way off to negative infinity. Typically, you don't go straight to negative infinity. You go all the way to like a negative very large number m. And then you send m to infinity. And you send t to infinity. And the idea is you show that the integral over the top becomes negligible. By symmetry, the integral over the bottom is negligible. As you move this to infinity, this becomes negligible. And so the integral along this line will then just be equal to the sum of the residues. Where are we going to get residues? We'll get residues from the zeros and poles of zeta. There's a pole of zeta at s equals 1. And then it's believed all the other zeros either have real part 1/2 or they're actually at the negative even integers. So we'll see later why they come from the negative even integers. The Riemann hypothesis is that all the zeros between 0 and 1 have real part 1/2. This is the greatest aside in any math paper. Riemann wrote one paper on the function which bears his name, and he remarks, just as an aside at the end of a paragraph, just like a sentence, it's like natural from symmetry or something like that, that all the zeros lie on the line 1/2. But since it's not needed for the present purposes of the paper, after some brief attempts, I have put it aside. Riemann actually calculated at least the first 6 zeros of the Riemann zeta function by hand and showed that they were all on the line. So it's an interesting thing as to how do you actually prove it's exactly on the line? And that's an interesting question. It turns out you can find a function that has the same absolute value as the Riemann Zeta function, but is real valued on this line. And you can look for sign changes. And if you ever get a sign change, you know how to have a 0. By doing the argument principle, you can count the number of zeros. He actually had the first 6 zeros. He had a formula for this, which was lost for about 70 years. And then somebody was going through Riemann's papers in the old Göttingen library and actually found Riemann's method, which was better than what people had been using. So absolutely remarkable what was known and what was put in the paper. Let's look and see what would happen if we do the calculation. OK, so assuming that the integral over all the sides and everything cancels, then we get contributions from the zeros and the poles. So the first is when we have a pole at s equals 1. The function x to the s over s is fine except at s equals 0. That's the only place where that's bad. So we get a contribution of x. And this is from the pole at s equals 1. Now as we move the integration to the left, we get a contribution over all the zeros of the zeta function. Turns out there's no other poles. So then we get a minus a sum over rho, zeta of rho equals 0. And we'll get x to the rho over rho. We have to be a little bit careful here. The imaginary part of rho is going to be less than t. It's very important that we do a sum like this symmetrically. It turns out the sum of the reciprocals of the zeta function diverges. But if you do them symmetrically, you have some cancellation from sign, and the sum will converge. This is meant to be a high-level overview. If you think about this, if all of these are of size, real part 1/2, or a negative even integer, well, negative even integer, that's going to be a negligible value of x. X to the negative 2, x to the negative 4, x to the negative 6, insignificant in the limit. If they're all 1/2, then this is of size x, this is of size square root of x, it's much smaller. And then this should equal the other integral. So it turns out when you integrate x to the p over to the s ds over s, this is a beautiful, beautiful function. If you want a nice exercise, that's a great integral to try to do. We will have to do that integral later this semester. It is an indicator function. It doesn't look like it, but it turns out that function is 1 whenever p is less than x. It is 0 if p is greater than x. And I will leave it to you to ponder what happens when p is exactly equal to x. What could we do to make sure we never have to worry about the case when p is exactly equal to x? So it's 0 if p is greater than x. It's 1 if p is less than x. I don't want to worry about what's going on when p is actually equal to x. So what can I do to make sure I never have to worry about that case? What should I do for x? What value should I take for x? Well, I want x to be a large number, because this is going to look like the sum over all primes less than or equal to x of log p. Yeah, take x to be an even integer. Or take x to be an irrational number. Do any small little thing like that. So this is the main term. It's going to give us the sum of primes less than or equal to x plus smaller. And so now when you look at this, yes? Yes. Because remember, p is always a prime. So this is you using the integral over, real part of s equals 1 plus epsilon of x over p to the s ds over s is equal to 1 if p is less than x, 0 if p is greater than x. And I'm not going to write down what happens when p equals x because I don't need it. So this is a way to detect primes. And notice it's detecting primes with a log weight. And where is the log weight coming from? It's coming from the Euler product. It's coming from differentiating the p to the minus s. So what I like about this is you begin to see why logs are coming in for the primes. They're coming in a very natural way. It's coming in from a logarithmic derivative. And so if this is really much smaller, it's telling us the sum of the primes less than or equal to x is about x. So basically, the sum over primes less than or equal to x of log p is about x. And now you want to pass from that to what can you say about the sum p less than or equal to x of 1? How large should that be? So this is where you could use partial summation. You could write this as log p times 1 over log p. This would be a function you could differentiate. And then we know from above what this is, and you could use partial summation. The other thing you could do is you could try to get you some rough estimates. Okay? And so I won't get quite as good, but let me just give you a really crude estimate to show you how you can get these order of magnitude growth rates. And then we'll see why we need to do more work. So this is the sketch of the proof of the prime number theorem. The challenge is justifying some of the steps. If you remember when we were actually doing explicit integration, the challenge sometimes was showing that the integral over this arc was small, and sometimes we had to say, well, if we stay away from this little bit of an angle over here, then we have some decay that we can exploit. And we need to be able to make sure that these bounds are small. Right now, we don't even know if the Riemann Zeta function makes sense when the real part of s is less than 0. So doing something like this, I don't even know if the function's defined. We need a better extension. Otherwise, we would have to integrate along the line real part of s equals 0 or something like that. Okay? Later in the semester, I will show you a proof of the Riemann hypothesis that I came up with a few years ago. Not surprisingly, it is fundamentally flawed, but it illustrates how easy it is to make mistakes in these subjects and to assume something is reasonable. So I'm not going to alert you to look for a mistake. When you see proof of the Riemann hypothesis, you should know something is up. Okay? But so the real issue is we need a better extension, because we want to push the integration so far to the left that we have decay, and we can say the integral over that strip is insignificant. Calculating the integral of this part on this line is not bad. Calculating the contribution of the higher primes, not bad. That can all be done. It's just bookkeeping. The challenge is pushing this over. All right, so let me just end by talking a little bit about how we can go from this to summing primes at the end of the day. A lot of times, if you have a choice, you do the easier calculation. How many of you have done statistics? Okay, how do you measure errors? How do you measure errors in statistics? Do you look at signed errors? So if I want to try to find the best fit line in statistics, if I use signed errors, well, let's see. Here's 2 points. The best fit line for these 2 points is the following, because this positive error cancels out perfectly that negative error, and there is no error in my line. And that is the best fit line through these 2 points. If I used signed errors, this is a legitimate candidate. This is bad. Okay? Signed errors are bad. Okay? What do we use instead of signed errors? Take the square of the errors. Okay? There is another school instead of the square of the error. What is absolute values? If I'm hired as a consultant, I use the square. Because if I use the square, calculus is available, and I can differentiate the square function. If I'm hiring the consultant, I want the absolute value. Now, calculus is not available. They have to work a little bit more, but it's my money. Okay? Why do we like absolute values? It treats all errors equally. If you square, 1 error of 4 is much worse than 2 errors of 2. One data point that's bad can have a huge impact on the fit. And so there are issues with using squares as errors. But analytically, it's significantly more tractable. Okay? So whenever we're doing things, we always want to figure out what do we want to measure, what do we want to study, and why. So we are going to be putting in log weights, and I'm trying to give you a sense of why we're putting in these log weights. So let's look at the sum p less than or equal to x of log p. And we know this is about x. There's a lot of ways you can go about this. One thing we could do is we could look at the sum x to the 1 minus epsilon less than or equal to p less than or equal to x of log p. Now, in this range, what can you tell me about log p? So what do you know about log p in this range? How large could it be? How small could it be? Yeah, it's between log x and 1 minus epsilon times log x. So log p really isn't varying that much. So if I wanted to, as a lower bound, I could get it's greater than or equal to 1 minus epsilon log x times the sum x to the 1 minus epsilon less than or equal to p less than or equal to x of 1. Well, this is 1 minus epsilon log x, and this would be the number of primes at most x minus the number of primes at most x to the 1 minus epsilon. And we know that this is at most x. I could go the other way and I can get upper bounds and whatnot. I'm just going to try to get a lower bound for pi of x. So when the dust settles, I guess I'm going to get an upper bound. I'll get pi of x is less equal to x over log x with a 1 over 1 minus epsilon plus pi of x to the 1 minus epsilon. So the prime number theorem is that pi of x is about x over log x. Can anybody give me a crappy bound for the number of primes at most x to the 1 minus epsilon? I will admit x is a crappy bound. It is just too crappy. Can you improve it ever so slightly by epsilon, say? What is a slightly better bound for the number of primes at most x to the 1 minus epsilon? I'm sorry? Oh, this is a tough day. But I asked you to improve by epsilon, and that's only improving by 1. X to the 1 minus epsilon, right? Worst case scenario, every number up to x to the 1 minus epsilon is prime. So this will give us pi of x is less than or equal to x over log x 1 over 1 minus epsilon plus x to the 1 minus epsilon. Well, x to the 1 minus epsilon, this is the same as x over x to the epsilon. For any fixed epsilon, this is much, much smaller than x over log x. And so you can begin to see where you're getting the x over log x. And then you can try to find, OK, this gave us a upper bound. Can we get a lower bound? A lot of times the way people will do this is they'll do it as a dyadic sum. So what they would do is they would do the following. The sum p less than or equal to x of log x, this is equal to the sum x halves less than or equal to p less than or equal to x of log p plus the sum x fourths less than or equal to p less than or equal to x halves log p plus dot, 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 dot. And before, we got a lower bound. So now what we would do is we would do an upper bound. And so we know basically x is like this. So this would then be less than or equal to get an upper bound, this would be a log of x. And then this would be the sum of the primes between x and x halves. So this would be pi of x minus pi of x halves. The next piece would be the log of x halves, pi of x halves minus pi of x fourths, plus dot, dot, dot. And there's not that much difference between log x halves and log x. And you can start trying to play games with this and see if you can isolate something out. So the idea is also use the log p times 1 over log p is 1 and partial summation. The idea is if we can understand the sum of log p, we can pass to get the sum of just 1 and just count the primes. So it turns out it's easier to count the weighted sum, and once we know the weighted sum, then we pass to the sum we care about. So we care about the sum of just how many primes there are. You don't really care at the end of the day, how many weighted primes are there at most x? You care, how many primes are there at most x? Well, it's the weighted primes that's easier to handle. The other thing, which I'm not going to get into now, it's too far afield, sadly, is in a lot of modern analytic number theory, you would never do this. You have a sharp cutoff. Either the prime is less than x, or it's greater than x. And if it's less than x, we count it with this log p weight, and if it's greater than x, we don't count it at all. Sharp cutoffs turn out to be very hard to handle analytically. It's much better to have smooth, continuous cutoffs. They can be rapidly decaying, but it's much easier if you do things continuously. Now, in many things in life, you can't do things continuously. You know, congratulations, we've decided to admit 93.2% of you to Williams. You know, you are not going to have something like that. You're either in Williams or you're not. You know, the Los Angeles Dodgers, they lost to the Astros 4-3. They don't get 12% of the World Series championship. They get nothing. Okay? A lot of things in life have a hard cutoff. And we often want the hard cutoff. But it's actually the smoother cutoff is frequently easier to understand. And then sometimes you try to pass from the smooth cutoff to the clean one. All right. So now we're going to pivot. And if we want to improve our understanding of the Riemann Zeta function, we need a better analytic continuation so that we can finish this argument. And to do this, we're going to need the gamma function. For a long time, we had results that were close to the prime number theorem, but not. Chebyshev came extremely close. In 1852, he proved that the number of primes at most x is at least 0.9x over log x, and it's at most 1.1x over log x. And he proved that if pi of x over log x converges in the limit, it converges to 1, but he couldn't prove it converged. And you could refine his method to get as close as you want. He basically came as close to proving the prime number theorem as possible without actually doing it. I have never been able to convince people to do this. There's at least 40 different ways of spelling Chebyshev's name in English from Russian. I would like to use a different spelling for each theorem of his. So he has so many theorems that when you spell it this way, oh, it's the probability theorem. If you spell it this way, it's the number theory one. So almost any way you spell his name is correct. It's amazing. People begin to think, this was in the 1850s, in 1896, we finally proved the prime number theorem. It was Hadamard and de Vallée-Poussin at about the same time, using complex analysis and developing tools from complex analysis to prove the prime number theorem. So a lot of times in math class, you just boom, 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 you're like machine gun list of theorems. The motivation for a lot of the results in complex analysis came from trying to count primes. It was felt unsatisfying. I want to count integers. Why am I in the complex plane? I want to count numbers. So it was felt that after a while, there's no elementary proof of the prime number theorem. It's fundamentally a statement about the Riemann Zeta function, its continuation, its zeros. And we came up with two conjectures. You can't prove it elementarily, and if you can prove it elementarily, boy, will that illuminate the subject. Both are wrong. And there's a really interesting story between, this is being recorded, so I'm not going to say, I will just refer you to a nice article describing the controversy between Erdős, Selberg, and the elementary proof of the prime number theorem that came around 1950, where it was discovered a way to prove it elementarily. It gives us much less than complex analysis, but it is possible to do it elementarily. If you want, think of this as very similar to divide and conquer versus Newton's method for finding roots. Newton's method uses calculus, and every time you iterate it, you double the number of decimal digits accuracy. Divide and conquer, you have your error, so it takes 10 iterations to get 1 over 10 to the 24th, or 3 more decimal digits. Why does Newton's method beat the hell out of divide and conquer? Because it uses more information. It uses calculus. It uses differentiability. Similarly, complex analysis is using a lot more than these elementary proofs. So the gamma function is going to play a key role in coming up with a good continuation of the Riemann Zeta function. So it is defined as the following. Gamma of s is equal to the integral from 0 to infinity of e to the negative x, x to the s minus 1 dx. And the first thing you should notice when you see this is the way it's defined. Why the hell would I define it as an s here and an s minus 1 over here? So you can also write this as x to the s dx over x. And if you write it like that, there's actually a meaning for something like this. If I rescale x by a factor of 5, dx over x is invariant. This is really looking at a transform with respect to a multiplicative measure. There are people who define a modification of the gamma function where you shift things by 1, and you call that g of s. All right, so we will look at this. So the first thing is you have to make sure that this integral converges. As x goes off to infinity, this has exponential decay, and no matter what s is, it's at worst polynomial growth. So the convergence as you go to infinity is no problem. So gamma of s, the integral is OK as x goes to infinity because of exponential decay. As x goes to 0, what do we need for this integral to make sense? What does e to the negative x look like as x goes to 0? It looks like 1. So I have x to the s minus 1. If I want this to be integrable, I need s to have real part greater than 0. Need real part of s greater than 0. And as long as the real part of s is greater than 0, this integral will make sense. All right, so it turns out, if you do the calculation, what is the easiest value of s to take? 1. If you take 1, you get gamma of 1 equals 1. Building on our success, if we take 2, we also get 1. All right, we have 2 data points, 1, 1. What do you think the next one should be? So it seems like it should be 1. It turns out it's the Fibonacci numbers. Gamma of 3 is 2. Well, maybe it's not the Fibonacci numbers. Gamma of 4 is 6. So if you haven't seen this before, 1, 1, 2, 6, what do these look like? Factorials. 0 factorial, 1 factorial, 2 factorial, 3 factorial. It turns out gamma of n plus 1 is n factorial when n is a positive integer. So I'm going to just do the proof somewhat quickly. We'll do it by induction. Gamma of s plus 1 is the integral from 0 to infinity e to the negative x, x to the s dx. All right? This is screaming integration by parts. And I have e to the minus x. I can integrate or differentiate. It's not going to really matter. Since I'm trying to reduce this to an earlier one, I probably want to lower the power of x to the s. So I'll take u equals x to the s. du is s, x to the s minus 1. Oh, beautiful. We want an s minus 1. That's looking nice. dv is e to the minus x dx. So v is going to be negative e to the minus x. And now when I do integration by parts, I'll get the boundary term. At infinity, I don't have to worry. And at 0, that's going to cancel out. The negative sign is going to reinforce in the integration by parts. And so I'll get gamma of s plus 1 is just the integral from 0 to infinity e to the negative x. The s I can pull outside, x to the s minus 1 dx. Or gamma of s plus 1 is s gamma of s. So this is called the functional equation of the gamma function. It relates its value at s plus 1 to its value at s, or conversely its value at s to its value at s plus 1. So what's nice about this is you can use this to extend the definition. Initially, it only makes sense when the real part of s is greater than 1. I'm sorry, greater than 0. If I take s equals negative a half, that's the same now as gamma of 1/2 divided by negative a half. That makes sense. And now we can have a definition of this. So again, when we talk about analytic continuation, it means it agrees with the original function where they're both defined, but the new one can have a different definition, a different value in other places. You've seen this before. So consider 1 plus x squared. This is 1 over 1 minus x if the absolute value of x is less than 1. So this is just the geometric series formula. The left-hand side makes sense as long as the absolute value of x is less than 1. What about the right-hand side? As long as x is not equal to 0. So what is 1 plus 2 plus 4 plus 8 plus 16 plus 32? What does this equal? This equals negative 1. When you add all the powers of 2, you shoot past positive infinity, come from negative infinity, and almost make it back to 0. How many of you have seen p-adics? P-adically, this actually makes sense. So if you think about what this means, if I add 1 to both sides, 1 plus 1 is 2, 2 plus 2 is 4, 4 plus 4 is 8, 8 plus 8 is 16, 16 plus 16 is 32. If you've seen the p-adics, this is actually going to just push you to 2 to the infinity, which is 0. So it really actually makes sense p-adically. There's a lot of wonderful stuff here. Later on, we'll see. Do you think this should be larger or smaller than the sum of the powers of 2? What do you think, larger or smaller? Come on.
Well, you're asking, so I'm going to go with larger.
Of course it's larger, right? You've got all the powers of 2. It's negative 1/12. Significantly larger. This is coming from looking at the Riemann Zeta function. There are ways to interpret things like this. There are ways to interpret these infinities. So this idea of analytic continuation, of taking something that makes sense in one range and coming up with a new function that agrees with it but makes sense in a larger range, is extremely important. This is what we're doing with the Riemann Zeta function. So what we want to do now is we want to apply something like this to the gamma function. The gamma function turns out to be related to a lot of things, not just the Riemann Zeta function. It's related to the moments of the Gaussian. There's a lot of beautiful results about it. What I want to do is, we have about 10 minutes left. I want to talk about Stirling's formula. We will eventually prove Stirling's formula using Laplace's method. If you've taken advanced physics classes, you might have seen Laplace's method, or method of stationary phase, to estimate integrals. So this is absolutely amazing. N factorial is the integral from 0 to infinity of e to the minus x, x to the n plus 1 dx. Here's a way to try to evaluate and estimate n factorial. Let's estimate this integral. We will learn techniques later in the semester to estimate this integral. A lot of it is you'll look for, well, where is the integrand largest? And then maybe hope that it decays very rapidly around the point where it's largest. So we will see later how to do this. What I want to do is I want to just talk about how would you estimate something like n factorial. This is just a good technique. So Stirling's formula, which we will prove later, is n factorial is about n to the n, e to the minus n, square root of 2 pi n, and then 1, I think it's either plus or minus 1 over 12n. I forget which way it goes. So you have some kind of expansion like this. The main thing is that n factorial is about n to the n, e to the minus n, square root of 2 pi n. So we've got 10 minutes. I want to talk a little bit about how we would estimate this and leave you with a problem for extra credit to see if you can push this argument and make it rigorous. So we have n factorial. So We seem to have a lot of smart asses today. Can somebody give me a lower bound for n factorial? I'm sorry? Okay, I was actually expecting 1. Can somebody give me an upper bound for n factorial? N to the n. Okay, so somewhere between 1 and n to the n. Let's do a little bit better. So we're going to use this method called dyadic decomposition. This is one of my favorite methods in math. And then I'm going to just assume that n is a perfect power of 2 if necessary. All right? So what I'm going to do is I'm going to break things in half. All right? So I've split all my factors. Now, for this stuff over here, I could approximate this by using 1 and then using n plus 1 over 2, which is about n halves. I'm not going to worry. So this would be 1 to the n halves, and then n halves to the n halves, less than equal to n factorial, less than equal to n halves to the n halves, and then n to the n halves. So do you have Mathematica on your computer? Yeah. OK, if you want to just load it up so you can calculate a few things quickly for me as necessary. So over here, what do we get? We get n to the n halves, and then we get 1 over the square root of 2. So we'll get square root of 2 to the negative n. Will be less than equal to n factorial. And the upper one, n to the n halves, n to the n halves, is n to the n. And then I'll have 1 over, so I'll have square root of 2, I think, to the negative n. So that's not so bad. What could we do to do better? Yeah, I could decompose it into 4 pieces. Then decompose it into 8 pieces, then 16 pieces. And to some extent, eventually, we're almost going to be seeing the n factorial coming in this decomposition. Now, another thing you could do is in this block, I don't know if you've called this, how many of you ever read Click Clack Moo when you were young? Farmer Brown has a problem. His cows like to type all day long. So when I teach calculus, I actually bring in the book and read from it. So the Farmer Brown problem is Farmer Brown is obsessed with rectangles. He can't stand anything that's not a rectangle. And if you have a fixed perimeter, what is the maximum area Farmer Brown can compose that's a rectangle? And it's a square. So you say you have x here, you have y here, so you have x plus y equals p. So you want to maximize xy, so you want to maximize x times p minus x. And this is just a parabola. It's 0 at 0, it's 0 at p, and you see the maximum is at p halves. As a nice aside, sometimes you have Farmer Brown's cousin or brother, Farmer Bob, and Farmer Bob lives with a water and only has to do 3 sides. And the fastest way to do this is Aquaman is at the same time trying to enclose a pen for fish. And now you have a rectangle with twice the perimeter. And so you see that this whole thing has to be a square. So in this case, it's got to be a rectangle where this is half that. So if we use the Farmer Brown problem, if you have a product with a fixed, with a summons, or I'm sorry, if you have a product where the 2 pieces have a fixed sum, the maximum is when they're each half. So when I now look at 1 to n halves, 1 times n halves is going to be less than or equal to n fourths squared. So I'm only going to work on the upper bound, but now I can play some games like this. And so I'll have 1 dot n halves plus 1 dot 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 n. And now I have n over 4 products. And each product is at most n fourths squared. So I'll have n fourths squared, and then I have that n over 4 times. And in these ones, it's going to be 3n over 4 will be the middle one. And I have n over 4. You can play similar games for the lower bound. In the interest of time, I will do the upper bound. What do we get? All right, we have n to the n halves, n to the n halves. So we get the n to the n as we want. Great. And now this is where I'm glad the student has Mathematica. So we have n to the fourth. So we've got 1 over 4 squared, and then we have 3 squared, 4 squared, right, to the n fourths. So this is going to be n to the n. If I take the fourth root of 4 to the fourth, that's 4. The fourth root of 3 squared is going to be the square root of 3. So this will be the square root of 3 over 4 to the n. So this will be n to the n, 4 over square roots of 3 to the negative n. Versus Stirling was n to the n, e to the minus n, square root of 2 pi n. So we have a 4 over square root of 3, which is?
Just that number.
Just that number. You know, e is about 2.718. 4 over square root of 3. 2.309. So not bad. All right? We've still got about 2.5 minutes. Let's lather, rinse, repeat. Let's do it again. I'm not going to write all the stuff on the board, so now I'll have n8ths squared to the n8ths, right? The next one would be 3n over 8 squared to the n over 8, and then 5n over 8 squared to the n 8, and then 7n over 8 squared to the n eighths. And then there's going to be a really nice thing that's going to emerge from this. Notice we're going to still have an n to the n. Down below, 8 squared, 8 squared, 8 squared, 8 squared to the 8th root, that's going to just be 8. What do we have up top? We have 1 squared, 3 squared, 5 squared, 7 squared. So we have 7 times 5 times 3 times 1. And then since it's squared, now this is going to be to the 1/4 power. And then we take this whole thing to the nth power. Now what's interesting about this is this looks like a factorial. So I will let you calculate this right now. So this is n to the n, and then we'll have 8 over, you actually write this as 7 double factorial. The double factorial means every other, to the 1/4 power to the n versus n to the n e to the minus n. So we need 8 divided by 105. And we need the 4th root of 105.
So negative power on the end.
Yes, it should be negative power to the n. Thank you. $2.499 versus 2.718. So the question is, if I continue this method, will it converge to E? You know, can you make this rigorous? Now, if I give you 2n minus 1, 2n minus 3, 3 times 1. I love multiplying by 1. Okay? So let's multiply by 2 to the n over 2 to the n. I'll multiply also by n factorial over n factorial. 2 to the n times n factorial, that's just all the evens. So this then becomes 2n factorial over 2 to the n factorial. So when you start having the product of all the odds, so 2n minus 1 double factorial is just 2n factorial over 2 to the n factorial. So you're actually bringing in the factorial, which is what you're trying to estimate. So for those of you who might have been, oh, you know, poor Chubby Chub, he was so close. You know, how can you get that close and not finish it? Well, here's my Chubby Chub challenge to you. I can make this as precise as I want. I can do upper and lower bounds. If I want to do lower bounds, I just shift over by 1, drop the first term or something like that. I can get this number as close to 2.718 as I want by just taking more and more things. Can you make it precise? Can you prove that it will converge to E? notice that what we're getting in is factorials. Well, if this is really, really large, we can approximate these with factorials themselves, right? If n is huge, then, so you have n huge, well, that will also be huge. So maybe you can feed this in, and can you actually make this work? So I will give massive amounts of extra credit for this. This could lead to a publication. This is your chance to try something. This is not something that will break any theoretical grounds, but it's nice to just see how far can you push a method. And you really want to get a flavor for that if you're going to do research mathematics. What am I leaving on the table? What else can I do with this? All right, so that is, I think, a good place to stop.